So yes, we started registration. Good afternoon, everybody. Good afternoon to the 10 person here in this room and to everybody else online. It's a pleasure this afternoon to welcome our guest, Matteo Teodori. Let me briefly introduce him, although you have seen it in these days. Matteo got his master degree at the University of Sapienza in astronomy and astrophysics with a thesis on gravothermal catastrophe and models from globular cluster with a mass distribution supervised by Marco Merafina. He earned his laurea summa cum laude on November 2020. No, 21. And in 2022, he worked on a stage at the INAF Observatory Rome on the mathematical techniques of the information field theory and their application to astronomical data, in particular with reference to shark quiz data for RBT. And since December, Matteo is doing his PhD at the University of Campania, Luigi Vanvitelli, under the supervision of Lucio Giaranella and our own Oscar Straniero. Today, Matteo will talk about the interconnection between multi-mass dynamical models and multiple populations in globular clusters. I'll give you the microphone and I will inform you in 20 minutes.
Thank you, Michele, for the very good introduction. Today I would like to convince you that there is this interconnection between dynamical models for describing multi-mass stellar systems and multiple populations in globular clusters. So let me show you the content. It's divided in two parts. The first is concerning these dynamical models. In fact, I would like to introduce them to you, and in their extension to multi-mass dynamical models, and also relating to the thermodynamic aspects of them. Then I would like to speak about the multi-populations and in particular the dynamical point of view. So let me start. So a brief introduction of globular clusters. They are stellar systems and are characterized by a dense center and a spherical shape. They're orbiting around galaxies, and our galaxies are something like hundreds of globular clusters. And they contain around 10 to the 5, 10 to the 6 stars. And the high density, in fact, make the gravitational encounters very frequent. And in general, they also host a lot of very old stars. And in fact, their age is around the age of the universe. So why do we study globular clusters? As I said, because they are ancient systems. And also because they are probably the only collisional system we know, because we actually do not know the information, and it is pretty interesting studying it. Because we, in fact, have to still to understand the evolution concerning both the stellar evolution and dynamical evolution, which is mainly connected to the evaporation of stars, because globular clusters use stars due to the galactic potential. Due to the effect known as mass segregation, which means that massive stars goes toward the center, and while light stars goes toward the other regions, mainly connected to the equipartition of the energy, because gravitational encounters lead to a sort of relaxed system, partially or fully. And as you may imagine, multi-populations can play an important role. There is a lot of stuff to understand in this sense, from their formation and their evolution and the role that they act in the globular clusters evolution. And finally, their stability, and mainly looking at what is known as the gravothermal instability. So let me say this is what we are going to speak about in the next slides. So introducing theoretically these the studies that were performed by King he found in 1965 that a solution to the collisional Boltzmann equation valid for stellar dynamics, which is known as the Fokker-Planck equation. And he found a distribution function with a cutoff in the phase space. For those who do not know, a distribution function is a function that describes a number of stars in the 6-dimensional space of positions and velocities. In 1966, he applied his distribution function to globular clusters, mainly looking at the surface brightness. You can see here the distribution function expression. You get here that Phi is the gravitational potential, and you have that this distribution goes to 0 when the velocity is equal to the escape velocity, which of course depends on the radial distance. And if I had this good agreement, this is only for a cluster, but the King model was used to fit all the known globular clusters of our galaxy. And the agreement is quite very good until in 1976, Da Costa and Freeman were studying the M3 cluster. And they obtained that the King model, which is able to produce a surface density profile, was not able to reproduce the curves of the surface brightness, both in the inner regions and the outer regions. So you get here two models that can be can describe the singularly these regions. And they introduce a discrete model with multiple masses. In fact, each of their mass classes, in fact, were a distribution function with an energy cutoff. You can see here, this is the expression. And you get these parameters, which in a dimensionalization lead to what I call the IE factors. And in fact, they are, we need to understand their shape to build the model. And they've done this, obtaining these curves for the surface brightness. Let me say that they need and use the knowledge of the relation between the light emitted by the stars and their masses, because without this, you can't fit the profile. So the main reason is, in my opinion, is this. Let me go on. Because in my master thesis work, I obtained that this distribution function of generical mass M can be written in a formally similar to the King one. But in principle, this is assumption that each mass can be described in the same way with a cutoff, a distribution function with a cutoff. So I would like to prove that a Fokker-Planck equation taking into account gravitational encounters with in a system with a mass distribution can lead to this solution. And in fact, it is like that. So following the literature approach that in fact lead to the King's model, and which was in fact based on the dynamical friction of Chandrasekhar so far. And so taking into account the relaxation of a star with mass M with all the stars that have a mass distribution, the other stars are indicated with MA. This leads to a new expression of the Fokker-Planck equation, this highlighted with a box, which rules in fact the temporal variation of the distribution function Fm, that is the distribution function of the mass M. I don't want to go much in details, but you can see that there is this ratio of the calligraphic G over TR that contains the information of the mass distribution and the integration over the so-called field star. And we also find that reproducing the King approach or writing the distribution function in a time-dependent part, which involves the evaporation rate, and a time-undependent part, which is connected to the equilibrium configuration, we can obtain the solution for the dimensionless part that is in fact very similar to the King distribution function. The evaporation rate is slightly different. And there is this wave function, which when applying the Jeans theorem, because this calculation is valid in the inner regions, so the Jeans theorem allows us to study and obtain the distribution function of the whole system, which appears to be an integration over the masses of another function that we identify to be king-like, as you may imagine, because here epsilon is the kinetic energy. And as this wave function, that in fact is very similar to the Lacoste and Freeman model. And this function is related to central values for the numerical density or escape velocity, but we still miss an analytical expression. And another interesting thing is that if you integrate this distribution over position and velocities, you get what is the mass function of the system. So both that wave factors and the distribution function contain information on the mass function. So we need to understand their role and how to do that. So if we take as a reference the connection with the Lacoste and Freeman model, which in fact allows us to study clusters, we can constrain both the I parameters and the W0 parameter. W0 is the central dimensionless potential wheel, and this expression is an extension of the king one, because it already has something like that. And to do so, we need the mass function and the concentrations. So taking a literature from the work by Ebrahimi and collaborators, the observed global mass functions of 32 globular clusters and the respective concentrations from the IRIS catalog, we in fact were looking for a relation between these parameters and the masses. So our model was calibrated on the observed mass function, which was assumed to be a single power law in the range 0 to 0.8 solar masses. And the fit function is a power law given by this the expression in the slide, where in fact you have 3 parameters. Instead, in fact, you have 2 parameters, not 3, because 3 is not independent. And the interesting thing is that not only you obtain a very good fit for each cluster, but you also obtain that the exponent b is linearly correlated to the slope of the mass function. And together with the correlation between the k parameter of the fit and the concentration, which we in fact have to consider until 1.4. We see this y because it's connected to the ground thermal instability. We can think to use this relation to constrain these parameters instead of doing a numerical procedure that can be very time-consuming. I also reported here a relation between these parameters and the discretization of our continuous function. And so, as I said, this is a preliminary and very simple way to constrain the model parameters. But in general, we still need to understand their shape and their role, in fact, in the description of the system. But they also play a role, I think, in this topic, that is the thermodynamic of globular clusters. And because with the single mass model, we can, in fact, study thermodynamics, because the Fokker-Planck equation has a solution in an exponential form for all equal masses. So, and when the exponential form contains an Hamiltonian, which has the kinetic energy, the gravitational potential energy, and the so-called effective potential, which in fact is playing the role of the tidal forces of the galaxy. And this distribution function, in fact, recovers the King model. And this allows us to study thermodynamics and the ground thermal catastrophe. That is instability, a thermodynamic instability that onsets between different regions of different values of the heat capacity. So in this model, you get that the heat capacity, you can study the heat capacity profile. you get there is an inner region for only some values of W0, we'll see it later, that has a positive heat capacity, an intermediate region that has negative heat capacity. And this is responsible of the so-called gravithermal instability. I think that this picture is more descriptive of the situation, because this is the so-called calorie curve. For clusters that has W0 greater than 1.35, you start to develop the negative heat capacity region. Then you have the values of W03, so clusters that have W0 less than 3 have positive total energy, because here there is the zero line, and which in fact is saying that the cluster is failure to disruption is unbound. And this is also confirmed by simulations performed so far ago. And then you have, in fact, that globular clusters with W0 greater than 3 can be bound, and they evolve until W0 6.9. That is a critical point for this instability to answers. And look at the W0 distribution, which can be obtained from the globular clusters of the galaxy, of our galaxy. We obtain that the distribution is asymmetric, and its maximum is exactly or very near to the critical point predicted by the model. And in fact, here you can see that the evolution of globular clusters is going faster, and they are in fact disappearing. And you also get that there are not so much globular clusters in the low W0 values. But this was for a single mass model. So what happens when you consider a mass distribution? An extension of the effective potential theory is still possible, but with a true initial mass function, you get that the total energy of the system is always positive. This is the red curve you can see for each equilibrium configuration, so for each value of W0. And this is quite a problem, because it means that the system is always unstable. Analyzing the M3 results, we see that the use a great contribute to the total energy from the light stars, the effective energy impact. And this suggests that probably there is the stars with different masses are playing different roles. And so I would like to understand what happens when one change the mass function. So taking again a single parallel mass function and changing the slope and the mass range, what happens to the total energy? So in general, if you consider light masses, so below 0.5 solar masses, and if the mass function is a steep mass function, or the mass range is wide, you get that the modulus of the total energy increases. Instead, if you exclude light masses, if you take a narrow mass range, and if your mass function is a flat mass function, you get that the total energy modulus decreases. And just to show a couple of cases, this is for the range 0 to 0.8 solar masses, and the curves are for different slopes of the mass function. And you can see that there are not so much there is not so much possibility to have negative total energy. And the picture is very different when changing the mass range very slightly from the previous to 0.3, 0.7 solar masses. And you can see that there here happens that you have a range of W0 in which the total energy becomes negative, so in which globular clusters may survive, may be bound. But of course, you get too much dependence, too much great on the mass function. And in fact, the conclusion is this one. So the mass function plays a fundamental role in the description of the stability, and which in fact the total energy problem is still open, and we need to address it to the future improvements. But we still miss a a description, a theoretical description for a lot of other dynamical processes that are ongoing in these systems, and which probably are very sure are also playing a role in the formation of those multiple populations. And so we need to we want to use this model and test it and probably improve to understand the multiple population phenomenology, which in fact is related to an interplay between the stellar formation and evolution and the dynamical evolution. So let's speak about multiple populations. We observing globular clusters, we see that there are chemical and photometrical anomalies. From the chemistry point of view, we get some anti-correlation between elements. I just do not want to go too much in detail, but in general, you get this so-called first generation that is formed from gas with a primordial composition, and then you get another generation or subsequent generations, which seems to be made of enriched material. And typically, in all globular clusters, you have this second generation that is helium-rich, nitrogen-rich, oxygen-poor, sodium-rich, and aluminum-rich. And you also get sometimes that instead of having the sum of CNO elements constant and no iron spread, which relates the so-called type 1 globular clusters, you also have the type 2 globular clusters that present variations of the sum of CNO elements and iron spread as element spreads. And there are also problems connecting to the lithium presence enhancements in these second generation stars. We see differences also in the photometry, seeing multiple sequences in the color Mindwood diagrams. And we see them now on all evolutionary states. So, in fact, this can be also connected to the chemical variations. In fact, here in the picture, you have multiple sequences that can be well fitted with isochrones with the same age, but different helium content. And this is connected to the helium spread observed in these stars. And we also observe it in the Magellanic Clouds clusters. So what is the origin of these second generation stars? So we think that they are connected to nuclear processes. So the first generation stars can pollute the cluster medium with enriched gas, and which in fact forms the so-called second generation stars. Among the stars that can do this, we have the asymptotic giant branch stars, and in general massive stars, fast rotating massive stars, very massive stars, or interactive binaries. We need them because we need high temperature to reproduce the whole chemical pattern. In fact, because of the CNO cycle, and in fact that some nuclear cycle can be activated only at very high temperatures. But all of these polluters need the so-called dilution. So in fact, looking at the picture, you can see that the yields of these models of these stars must be diluted with you do not see very well here the dots in the graph, but there are some dots here, and you need in fact dilution with a material which with a primordial composition, and this is true for all polluters. And we also see that there are correlations with structural parameters. In particular, we have that only massive clusters have multi-populations. There is a kind of threshold at 10 to the 5 solar masses, and there is also a threshold in age. So we see multi-populations only for clusters older than 2 gigayears. And the picture is quite similar if we include also the Milky Way satellites globular clusters, which are here the squares. And in red, you can see these regions in which multiple populations are present. Instead, in cyan, here is where you do not see multiple populations. We see that generally there is a correlation between the mass of these clusters and the chemical spreads. And as already said, these second generation stars are present in all the evolutionary states. So we looking at the fraction of these stars, we obtained that globular clusters are predominantly made of second generation stars. And this is not possible if you want to form them from the first generation stars. You have a mass budget problem. And the solution to this problem, the proposed solution, is that clusters initially were much massive than about something like 1 or 2 order magnitude. And then they lost preferentially first generation stars. In the plot, you have, in fact, the fraction of first generation stars and the correlation with the actual mass. And you have that a lot of clusters have not so much first generation stars. Of course, there is a trend, and the trend is also with the mass. So more massive cluster, more second generation stars it have. And here I present you a scenario that I think can be descriptive of the whole, what is happening in the world. That was proposed by Derkel and collaborators in 2008. And in fact, they assume that the polluters are LGB stars, which with their low velocity wind can pollute the interstellar medium. And performing a dynamical simulation for the formation of the second generation stars in the framework of the first generation stars potential and gravitational potential distributed according to a distribution function and profile impact, and considering that the polluted gas can be diluted with episodic mixing with this pristine material, and also considering supernova feedbacks, and let me say in general, additional energy sources, you obtain generally that the second generation stars are formed more concentrated because the star formation is more efficient. And this, in fact, can be used as an initial condition for studying the dynamical evolution, mainly with the M-body. So, in fact, you have this system made of 2 kinds of stars, and the second generation stars have initially a distribution much more concentrated than the first generation stars. And then you get 2 kinds of dynamical evolution. The first is the so-called early dynamical evolution, connected to the fact that stellar evolution triggers the second generation stars. Once they go in a supernova, they can dynamically hit the whole system, because they remove potential energy. And in fact, to reach again the virial equilibrium, the system expands. And the first generation stars, that are those which are well distributed inside the tidal radius, can expand over the tidal radius, and so they preferentially lose. And then you have the second evolution, the so-called long-term evolution, which is driven by two-body relaxation, and which mixes the cards of these multiple populations. And in fact, here you have in the plot, you can see how much the number of the first generation stars can evolve faster at the beginning. And then you have the long-term evolution, in fact, to which the evaporation is subtracting stars to both the first and second generation stars, but the rate is very small. And here, in fact, you have the evolution of the number ratio of long-lived first and second generation stars. And the beginning of the simulation is in black. And And then in red, you have the end of the simulation, in which, in fact, they are mixing, spatially mixing. So looking at these dynamical effects, and mainly the highlighted here, for example, evaporation, the interplay between evaporation and segregation, which can affect the global and local mass functions. We can study these effects. Also, we have that tidal forces can erase an initial rotation. So even if you have a cluster that initially rotates, the tidal forces to in fact extract angular momentum from the cluster. It can be partial or complete, but I do not want too much to go in detail about this. And you get also that there is the multi-populations and the initial difference, spatial difference triggers and produce radial anisotropy, which then is erased by this relaxation of two-body encounters. Looking at the primordial binaries, you expect that the first generation, and you see that first generation stars have a binary fraction quite very similar to the field stars binaries, and which is much more in number, in fraction than the second generation stars, because high density environment disrupts binaries. But the evolution of this, the fraction of binaries for the multi-populations is still debated and widely unknown. And then there is also this type 2 globular clusters that we do not know, in fact, if the different chemical spreads can be related to their formation, in fact, because we do not know if they are formed in situ and how was the primordial environment of their formation. And this is general for globular clusters. And I would like to spend some time about the highlighted topic in this slide. So mass segregation, as I said, is due to this relaxation induced by gravitational encounters. You get that massive stars relaxate toward the center regions and are also slower than the light stars, which relaxate in the outer regions and are also faster. And in literature, the mass segregation is studied using this function provided by Bianchini, which is in fact saying that the equipartition of energy can be not always complete. You get that it is complete only in the second case. And so in fact, what measures the degree of equipartition and mass segregation is this equilibrium mass, which means that if it is low, you have a high degree of energy equipartition. And as you may expect, in the denser region of the center, you get that M equilibrium is lower than in the outer regions, so it increases with distance. And since the initial properties, the second generation stars have this quantity that is lower than the first generation stars, and because second generation stars evolve faster. And looking instead at the mass function, you get that in a cluster, the global mass function can be flattened due to the interplay between segregation and evaporation, because segregation, as I said, brings light stars outside, and evaporation removes them. So the mass function, in fact, is depleted of light stars. You looking at the multi-populations and local mass function differences, there are some differences due to these differences in their relaxation process, because second generation stars relaxate and mix faster, and so they have a steeper mass function in the outer regions. These differences in the local mass function can be increased with a different initial mass function. But this is valid if you do not consider any primordial mass segregation, which means that when they formed, the system was already segregated, which can instead affect the global mass function and the local mass function. In the picture, you see the evolution of the mass of second-generation stars with respect to the total, and in the x-axis, you have the slope of the mass function of long-lived stars, so in the rate 0.3, 0.8 solar masses. And this is the first part of the plots is the early evolution. Since you do not have an primordial mass segregation, the early evolution, so the preferential loss of first-generation stars, is not modifying the mass function. And so you get that this quantity increases, and then the mass function floods to tends to 0 for all the simulation performed in this work by Vesperini and collaborators. And looking at anisotropy, you can see that if you initially set up the two populations both isotropic, the second generation becomes anisotropic due to the initial spatial differences, and these differences are raised during the evolution. So, for example, in the first plot, you can see that the anisotropy profile, radial profile for both populations. In red, you have the first, and in blue, you have the second. And it is quite similar because here the complete mixing is reached. Instead, in the second plot, you can see that the second generation is radially anisotropic because the clustering space is not so much evolved. And instead, if you have any degree of initial anisotropy, you can see any difference in the even nowadays. And so, in general, we have to understand all the evolutionary path of these globular clusters and characterize these phenomena that are occurring both from the stellar evolution point of view and from the dynamical point of view. And I think that in this sense, there are some studies which are not looking at multiple populations that can be very interesting. For example, the first one is this. Yeah, in fact, it's not the only one. It's just probably the last, and which is connected to the bilateral relaxation phase. So bilateral relaxation is a dynamical phase in which a system that is out of virial equilibrium in fact collapse and reach this virial equilibrium, so an equilibrium between kinetic energy and potential energy. And in n-body simulations of multiple masses systems, you get that the system arises from this phase with mass segregated, with internally rotating, and with radial anisotropy. And focusing on the mass segregation aspect, you also expect mass segregation from the so-called long-term evolution. And so it is quite interesting that a system arises from this faster, because bilateral relaxation is faster than the relaxation from two-body encounters in globular clusters in the long-term evolution. And you have this typical time scale that is the free fall time. And the interesting thing is that mass segregation can develop on local scales and earlier than this time. So this is the typical time scale for the collapse of the whole system. The whole system reaches maximum density and minimum in the dimensions. But instead, massive stars that we are in violet can collapse, in fact, in clumps, in where they are already segregated and faster. And this is, in fact, saying that this time depends on the mass. And in fact, you can see that looking at the half mass radius in terms of the Jacobi radius, this is the free fall time. So when the system has reached this minimum distribution, and then you can see that the system rises very soon with a degree of mass segregation. So the heaviest mass, the violet one, are more have a half mass radius more smaller than the light masses, which are here. And there is also another other works in general, which look at the formation and the effects on the dynamics of stellar remnants. And for example, there is this work of Wong and collaborators that in fact is study the long-term dynamical evolution and they found that this evolution is strongly affected by the supernova cake models, which in fact allows to retain or not black holes and neutron stars. In their simulations, black holes are retained and they affect the dynamics. For example, they can identify if a black hole subsystem is formed in the central region from their the fitting of both the surface brightness and velocity dispersion profile using a single mass distribution function. And even here, you obtain that the black holes segregate faster than all the other stars. In fact, in these simulations, only black holes were segregated. And then look at the profiles. You can see in the top panels, you have on the left the projected profiles, in which you can see anything particular. But in the three-dimensional profile, and I'm mainly referring to that of the velocity dispersion, you get that there is an inner region where the velocity dispersion decreases, and this is because this line indicates where the effects of the black holes can be obtained, and this is because black holes are high mass, so their velocity dispersion due to the relaxation and equipartition is lower than the other one. And but you can see this only in the three-dimensional plot because the projected profile you also see other stars. And so I'm almost reaching the end. And where do our model can use for example, we can use the model that is described in the first slides to set up multi-populations initial conditions for performing n-body or Monte Carlo simulations, because our model also contains information about the segregation. So we can simulate already segregated environments. We want to check if this model can describe the sequence of globular clusters as a sequence of equilibrium configurations, as was for the King model. And as I said, our model contains information about the segregation, so we can predict the mass segregation and the local mass function. So we can also compare with other works. And in general, we can use it to better understand how the relaxation time depends on the mass. And so, in conclusion, we need to understand better the coupling between stellar evolution and dynamical evolution for the formation of and evolution of multiple populations. We can use our model, in general, theoretical models to, they can be a strong tool to understand what is going on. And but our model actually must be improved in general, for example, because you do not consider any anisotropy. I think that there is a lot to understand in the early evolution of globular clusters, also connecting to the viral relaxation phase. And we need to understand, in fact, what's the real role and complete role of the stellar evolution and the remnants treatment. In fact, there is this strong dependence on the supernova cake models. And also, there is another thing that I do not develop at all, but we do not know the environment in which these systems are formed. So we do not know, in fact, how was the galactic potential 12 giga years ago. And And simulating it, there are simulations in which this galactic potential is a bit more realistic, and this can change a lot the picture. So also this is another point to address in the future. From the stability and thermodynamical point of view of globular clusters, we need to improve our description to, in fact, solve the total energy problem. And as I said, and I stress again, there are several processes occurring in globular clusters evolution, which lead to the formation of multiple populations, and they have a time scale, different time scales, which can also be mass dependent. And this is, I think, is one of the streamlining things in these systems. And so, that's all. Thanks for your attention.
I can. Yeah.